Hello and welcome. I'm Stephen Lyubomirsky from the University of Washington, and on behalf of my co-authors, it is my pleasure to present our proposal for addressing the mapping gap from high-level DSLs to accelerator-rich platforms. Custom accelerators can allow applications to reach new heights of speed and power efficiency. The great promise of specialized hardware is there for the taking, if only you can deploy code to those accelerators. And that, unfortunately, is not as easy as it sounds. At heart, this is a compilation problem. We must identify the portions of high-level application code that are supported by accelerators and lower them to the devices. And to get a sense of how tricky that mapping can be, let us consider our motivating example, FlexNLP. FlexNLP is designed to accelerate natural language processing tasks. It implements entire recurrent neural networks in hardware. Where most deep learning DSLs express models in terms of individual tensor operations, a single FlexNLP operation corresponds to an entire model. Additionally, FlexNLP is programmed using AXI commands over memory mapped I/O with a custom protocol to assign values to buffers. That requires the compiler to deal with the dramatic granularity mismatch between the high-level application and low-level hardware details. And as if that weren't enough of a challenge, FlexNLP also features a custom numerical data type called adaptive float. All of that knowledge has to reside somewhere in the compiler. And these are emblematic of the compilation challenges posed by accelerators. Every aspect of interfacing with the device requires special handling. So should every new accelerator require a bespoke compiler add-on? And while we're at it, should we manually tune and annotate applications for every new accelerator as well? If it's difficult to deploy new accelerators to applications, that poses a problem not only for those applications, but also for future accelerator development and the exploration of design options. In our paper, we propose to tame the varied design space for accelerators by introducing a uniform and formally specified interface for accelerators using the instruction-level abstraction. An ILA model provides a formally specified lifting of an accelerator's operations in the form of abstract instructions that update the software-visible architectural state. This provides an ISA-like interface for a compiler to target. Just like when targeting a general-purpose processor, the compiler only needs to output an appropriate sequence of ILA instructions. These can then be straightforwardly lowered to the specific device's MMIO interface, keeping hardware implementation details out of the compiler stack. What's more, the formal semantics of an accelerator's ILA also provide a variety of useful simulation and verification capabilities via the iLang toolchain. This opens the possibility for end-to-end functional verification by verifying the mappings between the source language and the ILA instructions. But how do we map a high-level DSL down to these ILA instructions? The recent Bring Your Own Codegen interface in TVM provides part of the answer: syntactic pattern matching. BYOC matches syntactic patterns corresponding to accelerator operations and hands the matching ASTs to a custom code generator, which is free to generate arbitrary executable code that uses MMIO interfaces or launches a web server or does anything it wants. BYOC is very general and does not require modifying TVM's internals, but that generality also means that each BYOC integration is effectively a standalone compiler requiring expertise for every device. With the 3LA methodology, we propose to use the ILA with BYOC to introduce structure after syntactic pattern matching. We will use a BYOC extension to match patterns, output ILA instructions, and then lower those ILA instructions almost one-to-one to MMIO operations. The key is that the ILA gives us a principled intermediate representation. It abstracts away the details of the accelerator's custom interface and allows us to perform other reasoning and validation. Using the BYOC interface, we have implemented a 3LA prototype that can deploy TVM models to a FlexNLP implementation on an FPGA, as my co-author Thierry Tambe will show you now.
Hi, so this end-to-end demonstration is for a linear layer workload, starting from TVM, going through ILA, and then being accelerated on FlexNLP on a Zinc FPGA. So let's launch it. So Python flexlinear.py will launch this whole end-to-end process. So now here, TVM sends the input and the weights of the linear layer neural network to ILA, which then parses this data and tiles this data for the FlexNLP PE. And then later on here, ILA has invoked the FPGA, which will then compute this linear layer workload, and the results from this computation are printed right here on the left. And these results is eventually compared against the GVM software results. And you can see here the error is only 1.8%.
We see many opportunities to extend these capabilities. Incorporating semantic reasoning into the pattern matching phase could allow for identifying more opportunities to invoke an accelerator. Additionally, having formal semantics presents the prospect of one day being able to automatically generate many portions of this compilation stack. All of this can be unlocked just by deriving a high-level ILA model for a device. The possibilities for verification and automation excite us as we continue to explore our prototype, and we hope they excite you too. My co-authors and I thank you very much for your attention, and we look forward to discussing compiler support for accelerators with you. And please allow me to thank the Ada Center for supporting our work.